Hello, so I'm Chris January, and I'm a principal software developer with ARM. In December 2016, ARM acquired Alinea Software, and I spent the last 10 years developing tools and expertise in writing parallel codes, both correct and really, really fast. And our software is used on 20 of the top 25 supercomputers in the world. Of those 5 that don't, one of them is China's Sunway chip, which we don't support. Another one is embargoed by the US government. So there's 3 which are growth potential there. Okay, so Alinea, there's 2 tools in the Alinea suite, if you like. They're all cross-platform tools. There's Alinea Forge, which is a profiling and debugging suite, and Alinea Performance Supports, which gives you a high-level performance overview. And they're primarily for C, C++, and Fortran, so compiled native code, but I'll also be showing you them on Python today as well. I'm not going to go into a lot of details about the tools, so if you want to know more, you can come and find me over a beer later on. So a little bit about high-performance computing, and really this should be high-performance scientific computing. First of all, applications are really, really large. So large-scale applications are rapidly approaching 1 million cores. We expect to see this in the next few years. And that poses some unique challenges when it comes to scaling, because these are 1 million cores that are coordinating. They're not running independent things that don't really depend upon each other, but they're highly coupled. So they're very sensitive to the latency of communications. 1 extra nanosecond on a communication can make an enormous difference to how well an application scales, because latency is magnified by the scale of the application. And they use a mixture of different parallel paradigms. So you have multiprocessing, typically using MPI. You have multi-threading, typically using OpenMP, and GPU parallelism, typically using CUDA. And all 3 of those may well be used in the same application. And users are expected to debug all of this interactively from their laptop. And there are actually advantages to interactive debugging a highly parallel code. If you follow a scientific debugging methodology, where you, and you all should, where you form a hypothesis, you design an experiment to test that hypothesis, you collect some data, draw some conclusions, rinse, repeat until you fix the bug. Then interactive debugging enables you to test many hypotheses at once from the same session. Offline debugging, if you're submitting a job, waiting for it to finish, trying again, then you get 1 or 2 at a time. It's a much slower process. And one of the important things about the high-performance scientific computing world is that users are scientists first and programmers second. Programming is a means to an end. They don't generally get their kicks just out of programming. They want to get their science done. And so generally, performance is measured in amount of science done rather than anything else. So I'm going to show you some of the design decisions that we took with Alinea DDT to make it scale to 1 million cores. And this is work that we actually first released back in 2009. So we've been doing this for a long time. And then I'll show you some of the more recent work in our linear map profiler. So Alinea DDT looks like a typical interactive debugger. It's deceptively simple in that respect. There's a native client that runs your laptop. So Windows, Mac, Linux, and connects to a computing cluster over SSH. But actually then behind that, there's a scalable communications tree, a scalable overlay tree, which we construct dynamically at application launch time. And that's really important, because everything that we collect from the processes that we're debugging is aggregated up that tree. What we want to avoid is, if we're debugging 1 million cores, having 1 million messages hit the front end and then have to do expensive processing on them all to aggregate data. If we aggregate it up the tree, each tree node has a manageable level of data to aggregate. And that applies to stacks, variables, error messages, anything that we're going to send. So here's a couple of user interfaces that we designed for scalable debugging. And the key design principle behind these is to show the user a view of what all of their processes are doing without requiring them to drill down one by one into each process. So when it comes to showing the position of the program, the stacks, if you like, we actually merge all of the stacks into a single tree, what we call the parallel stack tree. And it's merged at the line level rather than the function level. So you can quickly see where all your processes are, and you can see if any of them are actually somewhere you don't expect, which is probably where you want to investigate. We also aggregate data and variables from all of the processes up the tree as well. So next to the values of the variables here on the view on the right-hand side, you can see there's a little spark line which has the rank of the process on the x-axis and the value on the y-axis. And this enables you to quickly see the distribution and the variance of the data. You can see if the values are all the same. You can see if there's some trend in the values. You can also see if you've got an odd one out, again, leading to another line of investigation. The devil is in the details, really. So if you actually want to see the individual values, you can click on one of those spark lines and bring up this window, which is the cross-process comparison window. And that enables you to see all of the values grouped by process or thread. And you can see each of the unique values and all the processes which have that value for that particular variable or expression. Complex expressions or even function evaluation are supported as well. Of course, that works fine if you've only got a small number of unique values. Potentially, with 1 million cores, each process or thread could have a different unique value, and then you've got 1 million unique values, and suddenly the view doesn't work so well. So we actually use a lazy fetch from the cluster to get that data. It's a 2-pass algorithm. We send one pass to scale up the data and see how much data we have, another pass to actually get the data lazily. Of course, again, that's not very useful to scroll through 1 million values, so you have to allow the user to actually find the value they were looking for. So conditional expressions enable you to drill down and find the outlying values or the outlying processes. This doesn't work for arrays, of course. We have an even more scalable view for arrays that enables you to visualize arrays in different projections. In scientific computing, arrays may have multiple dimensions, 2, 3, 4, 5, 6, 7, and also you have to work out how you're going to project those onto a 2D display. After linear DDT, we scaled linear DDT up to petascale systems. It was on the world's #1 system at the time. We introduced a linear map, which is a scalable profiler. It's built on the same platform as linear DDT, so it scales similar to a linear DDT. One of the principles in map is we want to show not just a summary of the data, but we also want to show how the data varies over time. So in a linear map, one of the design principles we have is we have lots of these time-based graphs, and they all share a common horizontal axis of time. Although we're collecting data potentially from millions of cores, it's no good if that takes up millions of terabytes of data on the front end. So actually, we aim for very small data files of 10 to 50 megabytes. And we do that by aggressively aggregating data and throwing away data from individual processes and just showing the data that the user is interested in, the data that's the outliers and the important things. There's no recompilation or instrumentation involved. So the whole point behind this is it's easy for the user to use on those existing applications, and they can just run it without having to read a long user manual to figure out how to use the tool. And that's important when it comes to tools because, as has already been said, if the barrier to entry for the tool, if the learning curve for the tool is too steep, users won't use it, even if it's going to help them solve their problems. Okay, so one of the other design principles about a linear map is that we show source code front and center. If a developer is profiling their code, the thing that they can change often is the source code. And that's why they're profiling the code, see what source code changes can I make in order to get better performance. And that's why a linear map has the source code as the main view in the profiling. Many profilers will hide this away. And again, as I said, we show time as a common horizontal axis. And then across the top here, you can see not just the time spent on individual source lines, but you can see a global view of other metrics that correlate in time. So we can see, for example, the memory usage, the network communications, how much floating point operations the program was doing. And one of the important things in order to make this extensible and as flexible as possible is to provide plug-in APIs. And again, as already been said, allowing people to plug into your tools enables people to use them for use cases that you didn't even anticipate. And you can go further and dive deeper into why individual source line, where the time is spent, say, on individual source lines. You can see how much time is spent in vector floating point or in memory access and so on. And you've got the global graphs I mentioned across the top. Well, that's all very well, and okay, I can show you the tools, but actually, what use are these in the real world? So I want to give you two real-world use cases for these to show how highly scalable tools can actually help solve real-world problems. So the first one is to do with preventing strokes. Now, I don't know if you know what a brain aneurysm is. It's not my domain at all, but a brain aneurysm is a bulge that results from the dilation of a blood vessel in the brain. And blood accumulates in the bulge, and then if that leaks, then that can be fatal. It's generally fatal in about 40% of cases. And in fact, 2 to 5%, it's estimated, of the population have an undiagnosed brain aneurysm. And when one is detected, it's very important to decide, should it be operated on? It's not always the best option. And if so, how and where? And often, you've gone into hospital because something has happened, perhaps it is just about to rupture or has ruptured, so you need an answer quickly, in minutes or in hours, and not days or months. And you can take an MRI scan of an individual, and you can build a 3D model of the brain. And it takes about 2 to 10 gigabytes of geometry data. And then you can run a simulation of the blood flow around the brain in order to work out, as I said, how should we operate and how to operate. And this application called HemORB is a brain aneurysm simulation. And we worked with the developers of HemORB as part of a part of an EC-funded project. When they wanted to deploy HemORB on a new supercomputing facility, when they did so, they saw an unexpected performance problem. And they ran it under a linear map, and they saw this blue-green sawtooth pattern that you can see at the top of the screen now. And drilling down further, they were able to isolate the portion of code which was to drill down to see the portion of code which was affected. And they found that MPI I/O was costing too much. Now, MPI I/O is nice in theory. It's the idea that if you have lots of parallel processes that all write into a file at the same time, if they're to communicate with each other about what I/O they're doing, then this should be, in theory, more efficient. But in this particular system, this new system had different I/O characteristics from the previous deployment. And by isolating that problem with MPI I/O and fixing it and changing the code in order to use the I/O in a different way, they were able to get a 25% speed up in production. There was another problem with this code. They wanted to run it at the full scale of this new machine and take full advantage of the facility. When they ran it at full scale, which is 49,152 processes, it safe-faulted. Well, that's pretty difficult to debug if all you've got is safe-fault on line, whatever. So they fired it up and then did EDT. They could see which line it was safe-faulting on. And here we can see the stack trace for that line. What they found was that there were some suspicious-looking values, variables. And drilling further into the line where the crash occurred, and looking at this expression here, this I times NT samples over NPs, we find that the inputs to this expression, they all look fairly sane. No problem there. But when we look at the output of the expression, we see there's been an integer overflow. And by fixing that bug, changing the data types essentially to longer data types, we're able to get a 16.5 times capability increase on the previous best, and that's a 16.5 times faster time to decision about whether to operate or not. The second example I want to share with you is in deep learning deployment. And researchers at the Pacific Northwest National Laboratory in the US have produced this clean wrapper around TensorFlow, which to do image classification on a cluster in parallel. And we wanted to deploy this on Amazon EC2 using the GPU instances to see how it would perform. But when we did so, it didn't perform anywhere near as well as we were expecting. And we weren't sure why this was initially, so we ran it in a linear performance reports to investigate. And there were a couple of hypotheses we had. One was that perhaps the networking is slow between the EC2 nodes. And they don't have low latency, RDMA-capable networking. Well, that didn't appear to be the issue. The network time was low, and it was low bandwidth. That obviously wasn't a problem. Another hypothesis was that the GPUs are just not very powerful, or they're misconfigured or something similar. Well, again, that's not the issue. The GPU utilization was very low, 8.5%, so clearly that's not the bottleneck. But the memory accesses were unusually high. 83% of the time was just spent accessing memory. So we dived deeper into what was going on here. And TensorFlow is a Python code that we're looking at in this case. Now, map can't assign time to Python lines in the way that it can to C, C++, and Fortran. But we can see that the spikes in memory allocation come from a function called array from object. You can see at the top of the stack view there. And we can match up the stacks with the Python code easy enough by hand. You can see there the top 15.2% time spent in array from object. And if we put the measurements against the Python code, we see an awful lot of time is spent in this phase. We've got 3 phases here. Phase 1 is to train the network. Phase 2, we share the weights and calculate the average. And then phase 3, we're going to rerun it to calculate essentially calculate the error and then report that back. And what we found was that the error reporting code was forcing TensorFlow to make multiple copies of the entire test data, the entire test set from Python to C, and then copy from C native memory to GPU memory. And this was obviously very expensive. So by changing the error reporting from every epoch to every 30 epochs, we were able to get a 2.2 times speed up just by reducing the progress updates. And it could be silly things like that that kill your performance. So it's important that it's easy for users to use tools and to check for these kinds of things. It wasn't quite easy enough, so Python support is on the roadmap. Okay, that's all from me. I will take questions later on after all the talks. Thank you very much.